Welcome to another edition of The Explainer. Today, we're going to completely transform the way you look at something you see all the time: fire. Humans have harnessed it for millennia, to cook our food, heat our homes, power our modern world. But how often do we actually stop and think about the sheer magnificent science happening inside a single flame? Well, today we're looking past the light and the heat, and we're dissecting the hidden physics and chemistry of combustion. Trust me, by the end of this explainer, you will never look at a flickering candle or a gas stove the same way again. Let's get right into it.
Here's a quick roadmap for our journey today. First, the magic of combustion. Second, the two types of fire. Third, we'll go inside premixed flames. Fourth, decoding flame colors. And finally, understanding diffusion flames. This step-by-step breakdown is really going to demystify the whole complex physics of fire for us.
Section 1. The magic of combustion, the engine of fire. Okay, let's dive right into this. To ground us, let's look at this foundational definition. In strict scientific terms, combustion is a process of rapid oxidation that generates heat. Now, you can absolutely have slow oxidation, like rust forming on a piece of iron, but that doesn't produce light, and it gives off very little heat. Combustion is rapid, and honestly, the most beautiful part of this definition is what it fundamentally represents. It's a transformation. Combustion is all about taking the potential energy silently stored in chemical bonds and violently, brilliantly transforming it into usable heat.
But to really harness that transformation, scientists and engineers rely on three converging pillars. First, we have thermodynamics, which dictates the energy balance and the actual temperature of the flame. Then we have chemistry, which governs the stoichiometry, the equilibrium, and the chemical kinetics, basically how the molecules are actually breaking apart and combining. And finally, fluid mechanics. This controls how the flame propagates, whether it's perfectly smooth or totally chaotic, and how the fuel and air physically mix together. These three completely distinct fields of science all crash together to create the single, captivating phenomenon of combustion.
Section 2. The two types of fire. Premixed versus non-premixed. Let's meet the two main characters in the world of combustion. These are our stars, premixed flames and non-premixed flames, which are also known as diffusion flames. The main distinction here, it's all about timing. In a premixed flame, the fuel and the oxidizer, which is usually just air, are perfectly homogeneously mixed before any reaction actually occurs. Think of it like baking, right? A premixed flame is like mixing all your ingredients into a perfect batter before you put it in the oven. But with a non-premixed flame, the fuel and the oxidizer only come into contact during the actual combustion process. It'd be like throwing your flour, sugar, and eggs straight into the oven and just hoping they mix together while they bake.
And what's wild is how these abstract concepts reveal themselves physically. If you see a transparent, almost ghostly blue flame, that's premixed. Because the fuel and air were perfectly mixed beforehand, the combustion is incredibly efficient and complete. On the flip side, we have our non-premixed flame, like a classic Jello candle. It's bright, it's super visible, and it behaves completely differently because the fuel and air are literally scrambling to find each other in real time.
So we can take those two mixing categories and cross-reference them with fluid motion to classify pretty much every fire in our world. It's like a giant puzzle. A flame can be perfectly smooth, which we call laminar, or it can be chaotic and swirling, which is turbulent. So a spark-ignited gas engine, that's a turbulent premixed flame. The Bunsen burner from high school chemistry, that's a laminar premixed flame. Meanwhile, an aircraft turbine uses a turbulent non-premixed flame. And that cozy wood fire or the candle on your table, those are laminar non-premixed flames. It's just incredible how neatly we can categorize the forces powering our world.
Section 3. Inside premixed flames. Inside the burner. Let's deconstruct exactly what is happening inside one of these things.
What's really interesting about this is how it visually maps the invisible journey of the gas. The classic Bunsen burner is honestly a marvel of fluid mechanics. The whole goal here is to create a self-sustaining propagation of a localized combustion zone. Let's just pace through exactly how this works step by step. First, gaseous fuel enters from the bottom into the mixing chamber. Second, because that jet is moving so fast, air is naturally entrained, or physically pulled, into the holes at the base. This gives the air and fuel time to perfectly optimize their mixing before they even reach the top. Third, this ideal mixture flows out from the top of the tube. But step 4 is the real secret. What looks like a single flame is actually a dual flame. There's an inner, fuel-rich premixed flame cone, and then an outer, luminous diffusion flame. That outer layer is where byproducts like carbon monoxide and hydrogen encounter the ambient room air to finally finish burning.
Now this proves something highly counterintuitive about that inner cone. You'd think the entire flame is just scorching hot everywhere, right? Well, experimental evidence shows us that the very center of the inner cone is actually a cool preheating region. It's full of unburned methane and oxygen that simply haven't reached ignition temperature yet. In fact, this preheating region is so relatively cool that you can stick a match head right into the center of the flame and there is literally no way it will ignite. It's only when the match is moved slightly to the side into the reactive outer cone that it finally bursts into flames. How cool is that?
Section 4. Decoding flame colors. The chemistry of light. Consider this next part your very own decoder ring for flames.
You see, we can actually read a premixed flame just by looking at it. Its visibility strictly depends on the fuel and the exact state of the molecules inside. The color you see in the outer cone is not random at all. It's a direct chemical readout. It reveals exactly what kinds of molecular species are excited, and even more importantly, it tells us the fuel-to-air ratio of the mixture.
The relationship between fuel and color is absolutely fascinating. If a flame is fuel-lean, meaning there's a ton of air and very little fuel, it glows a deep violet. This is due to large concentrations of excited CH radicals, or methylidine. If the mixture is perfectly balanced, which we call stoichiometric, you get that crisp, clean blue flame. Now, if we tip the scales and make it fuel-rich, the flame turns green. This green hue comes from high concentrations of C2 species, which are carbon atoms in hydrocarbon intermediates. And finally, if the mixture is very fuel-rich, it turns a bright yellow. Why? Because there just isn't enough oxygen to burn all the fuel, which leaves unburnt carbon particles that literally glow yellow-hot in the heat.
Section 5. Understanding diffusion flames. The everyday fire. Let's bring this back to the beautiful flames we're most familiar with.
So here is the absolutely crucial takeaway for a diffusion or non-premixed flame. There is no mixing chamber. The fuel and the air are completely separate. Because of that, the actual burning can strictly occur only at the exact interface where the fuel gas and the oxidant gas meet. And this means the speed and intensity of the fire rely much more on the physical rate of diffusion, how fast those gas molecules drift into each other, than on the chemical reaction rates themselves.
And this brilliantly illustrates that whole concept, the simple, everyday candle. The primary concern when designing diffusion burners is the geometry of the flame, which is controlled by the flow rate and type of fuel. But inside this simple laminar diffusion flame, there is an incredibly elegant and complex physical dance taking place.
Let's just step through the life cycle of a candle flame. First, the heat melts the wax, and that liquid fuel travels up the wick through a process called capillarity. Second, once it gets close enough to the heat, the liquid fuel is vaporized into a gas. Third, that gas drifts outward until it meets the oxygen in the room and oxidation happens in these very thin blue layers right at the interface. But here's the kicker, step 4. Because the oxygen has a really hard time reaching the center of that vaporized fuel cloud, a lot of the fuel doesn't burn completely. Unburnt carbon particles form inside the flame. The intense heat of the reaction makes these microscopic soot particles glow brightly, and that's exactly what gives the candle its signature warm yellow light.
It's truly amazing, isn't it? What seems like just a simple flickering light is actually this complex, multi-stage factory of thermodynamics, chemistry, and fluid mechanics, constantly balancing fuel, air, and heat. So next time you strike a match, or turn on your stove, or start your car, I want you to look at that spark and ask yourself, what kind of flame is powering your world right now? Is it a turbulent premixed flame driving your engine, or a laminar diffusion flame lighting up your dinner table? Thank you so much for joining me on this explainer. Keep your curiosity burning bright, and I'll see you next time.